CERN has uncovered matter behaving in ways it shouldn't. Particles nobody expected to find, and signs that some of physics' most trusted theories might be missing something.
CERN did not find a portal, a black hole, or a tear in space. What it found was worse for physicists, a number that refuses to behave. Deep under the France-Switzerland border, particles called mesons are dying in a way the standard model does not quite predict. The difference is tiny but stubborn. It has survived for more than a decade, appeared in more than one detector, and keeps pointing to the same uncomfortable idea: reality may have a rule we have not discovered yet. The most successful theory with a missing wall. To understand why this tiny mismatch matters, you have to understand what it is threatening. The Standard Model is not just another scientific theory, it is the most successful description of the subatomic world ever built. It tells physicists what matter is made of, how particles interact, why some particles decay, and how 3 of the 4 known forces behave at the smallest scales. It is so accurate that in some measurements, theory and experiment agree to absurd precision, not close enough for ordinary human confidence. Close enough that the difference between prediction and reality becomes almost invisible, and yet physicists have never been fully comfortable with it. That is the strange contradiction at the heart of modern physics. The Standard Model works brilliantly, but it cannot be the complete story. It does not explain gravity. It does not explain dark matter, the invisible mass-shaping galaxies. It does not explain dark energy, the mysterious acceleration pulling the universe apart. It does not fully explain why neutrinos have mass. And it does not explain why the universe contains matter at all. Because after the Big Bang, matter and antimatter should have appeared in nearly equal amounts and destroyed each other into light. So the Standard Model is like a perfect map of one room in a house. Everything inside the room is measured beautifully. Every wall, corner, and shadow is known. But the map does not include the rest of the building. Physicists know there must be more. They just do not know where the door is. For decades, they have searched for cracks in the wall. Most have vanished, but one crack inside rare meson decays has not. The machine beneath Geneva. The search happens inside the Large Hadron Collider, the 27-kilometer ring buried near Geneva beneath the border of France and Switzerland. Inside the machine, beams of protons are accelerated to nearly the speed of light and smashed together inside enormous detectors. The collisions recreate conditions that existed fractions of a second after the Big Bang, producing showers of particles that live for unimaginably short moments before decaying into other particles. Most of what happens is ordinary by the standards of particle physics, but every so often, something rare appears. At one point on the ring sits LHCb, the Large Hadron Collider Beauty Experiment. Unlike ATLAS and CMS, which are famous for broad searches like the Higgs boson, LHCb was designed for subtlety. It studies particles containing beauty quarks, also called bottom quarks. These particles are unstable, and the way they decay can reveal whether the Standard Model is missing something. LHCb is not looking for a monster standing in plain sight. It is looking for footprints at the edge of a lake. That is why mesons matter. They are fragile particles that live for only about a trillionth of a second. But in that tiny life, they can become laboratories for new physics. A meson can decay through a rare process where hidden quantum effects influence the final particles that come out. If an unknown particle or force exists, even if it is too heavy to be created directly by the collider, it can still leave a faint fingerprint in one of these decays. The particle does not need to appear openly. It only needs to tug on the process from inside the quantum loop. The penguin that became a problem. The competitor script's strongest detail is the penguin story because it gives the science a human doorway. In 1977, physicist John Ellis helped popularize the name penguin diagram for a certain kind of particle decay drawing after a bet involving the word penguin. What began as a joke became one of the strangest serious words in particle physics. Today, penguin loops are part of how physicists describe rare decays where particles transform through hidden quantum processes. That joke now sits at the center of a serious problem. In one rare decay, a B meson transforms into a K-star particle and two muons. The K-star then becomes a kaon and a pion. This is not a common death. It is rare, suppressed, and delicate, which is exactly why it is useful. The standard model predicts how often it should happen and what angular patterns the final particles should follow. The number that would not die. The latest LHCb analysis made the story harder to ignore. Using data collected across Run 1 and Run 2, the collaboration performed its most detailed look yet at the B0 to K star mu decay. The results showed a global tension with the standard model at about 4 standard deviations. In ordinary language, that means the probability of getting a result this extreme by random chance, if the standard model prediction is fully correct, is very small. But particle physics is not ordinary language. 4 sigma is not a discovery, it is a warning light. The official discovery threshold is 5 sigma, and there is a reason physicists are so strict. They have been burned before. A 4 sigma anomaly can be exciting and still vanish. A 5 sigma result can even be wrong if the hidden problem is not statistical but systematic. That is why the best physicists do not celebrate too early. They do something less glamorous. They attack their own result. They ask if the detector misread something, if the background was modeled incorrectly, if the theory prediction is incomplete, if an assumption slipped through unnoticed. That is what makes the B meson anomaly interesting. It has been attacked for years, and it still has not gone away. The graveyard of dead anomalies. The competitor script did something very important here. It slowed down and walked through the graveyard. That is what makes the story feel credible. If you only say, CERN found a crack in reality, it sounds like clickbait. But if you show how many times physics thought it had found a crack and then lost it, the current anomaly becomes more powerful, not less. It has to survive comparison with every ghost that came before it. The first ghost is opera. In 2011, an experiment in Italy appeared to measure neutrinos arriving from CERN faster than light. If true, it would have shaken Einstein's relativity and rewritten physics. The result had enormous statistical significance. Then the real culprit appeared: a loose fiber optic cable and a timing issue. The neutrinos had not broken the cosmic speed limit. The second ghost is the 750 giga-electron-volt bump. In 2015, ATLAS and CMS both saw a possible excess in pairs of photons, exactly the kind of signal that might point to a new particle. The theory world erupted. Hundreds of papers appeared in months. Then more data arrived, and the bump disappeared. It was not a particle. It was a statistical fluctuation. The lesson was even colder. 2 experiments can see the same ghost, and the universe can still be playing dice. The third ghost is muon G2. For years, the magnetic wobble of the muon looked like one of the best chances to break the standard model. The experimental measurement became incredibly precise, and for a while, the disagreement looked serious. Then improved theoretical calculations shifted the standard model prediction closer to the experimental result. The arc warning: there is one more ghost, and it is uncomfortably close to this story. For years, LHCb also reported anomalies in measurements called RK and related ratios. These tested lepton universality, the principle that electrons and muons should behave the same way except for differences caused by their masses. Then LHCb revisited the analysis. A subtle background issue had affected the electron side of the measurement. When corrected, the anomaly disappeared and the ratios returned to agreement with the standard model. It survived comparison with CMS. It has not become a discovery, but it has refused to become a ghost. The charming penguin problem. The most serious mundane explanation has an almost ridiculous name: charming penguins. These are effects involving charm quarks inside the quantum loops of the standard model. The name sounds like a cartoon, but the problem is brutally technical. When a B meson decays through these rare channels, ordinary standard model particles can create effects that are extremely difficult to calculate. If those effects are larger or shaped differently than expected, they could imitate the signal of new physics. This is where the battle stands. Experimentalists can keep collecting data, but data alone may not solve everything. Theorists must also sharpen the predictions. If the standard model calculation is off because the charm contribution is not fully understood, then the crack could close without any new particle being needed. What could be inside the loop? If the anomaly is real, physicists already have suspects. One possibility is a new force carrier, often called a Z-prime boson. It would be like a heavier cousin of the Z boson already known in the standard model, but with new rules about which particles it talks to. If such a particle affected muons differently or influenced beauty to strange quark transitions, it could shift the angular patterns in rare B decays without showing up easily in direct searches. Another possibility is a leptoquark, a hypothetical particle that connects quarks and leptons. Quarks make up particles like protons, neutrons, and mesons. Leptons include electrons, muons, and taus. In the standard model, these families are separate in important ways. A leptoquark would blur that separation. The hardest part is that new physics must explain the anomaly without breaking everything else that the standard model already gets right. That is like trying to repair one tiny crack in a glass sculpture without touching the rest of the glass. Any new particle must be powerful enough to bend the B meson decay, but subtle enough to hide from decades of other measurements. The flavor puzzle. The original twist for this version is that the crack may not be random. It appears in the part of physics where the standard model already looks unfinished: flavor. In particle physics, flavor refers to the different types of quarks and leptons. The weird thing is that matter comes in 3 generations. The electron has heavier cousins, the muon and the tau. The up and down quarks have heavier cousins too. These copies have the same basic charges but different masses, and the standard model describes them without explaining why the pattern exists. That mystery is called the flavor puzzle. Why 3 generations? Why these masses? Why do particles mix and decay in the particular ways they do? The standard model gives rules, but not the deeper reason. So if new physics were going to appear somewhere, flavor would be a natural place. Rare B decays are not just obscure technical processes. They are tests of how one generation of matter talks to another. That is what makes the anomaly feel like a draft under the door. It is not appearing in a random corner. It is appearing where physicists already suspect the wall is weakest. The standard model can describe flavor, but it does not explain it. And now, one of the most precise flavor laboratories on Earth is finding a stubborn lean in the data. Why getting worse does not mean what people think. The title says the crack is getting worse, but in science, that does not mean reality is falling apart faster. It means the anomaly is becoming harder to ignore. A strange result can become less important when more data arrives and pushes it toward the standard model. That has happened many times, but this one has not followed that path. It has lingered. It has become better measured. It has been tested by different teams. It has survived the collapse of nearby anomalies that once seemed connected to it. That is why physicists are careful but alert. The crack is not widening like a movie fracture across the sky. It is worsening in a more subtle way. The escape routes are narrowing. Instrument error became less likely when another experiment saw a compatible result. Pure chance became less satisfying as the pattern persisted over many years. Simple background problems became less convincing after repeated reanalyses. The theory loophole remains, especially the charm contribution, but even there, the pressure is growing. This is what real scientific suspense looks like. It is not a single dramatic announcement. It is a slow tightening. A measurement gets repeated. A prediction gets improved. An alternative explanation weakens. Another experiment checks the same process. The anomaly does not explode. It endures. The next test. The next stage belongs to more data and better theory. LHCb has been upgraded for Run 3, and future datasets will be much larger. CMS and Atlas will continue to test related processes. Bell 2 in Japan can also add important measurements in a cleaner electron-positron collision environment. Meanwhile, theorists will keep attacking the charm problem, trying to calculate whether the standard model can still explain the lean without new particles. If the anomaly fades, physics will learn something. It will become another grave in the cemetery, another reminder that nature does not owe us a breakthrough. But if it strengthens to 5 sigma, if the charm explanations fail, and if related decay channels begin pointing the same way, then the story changes completely. The standard model would not be destroyed. That is not how science works. It would become what Newton's laws became after Einstein. Still useful, still brilliant, but no longer the final word. That is the real meaning of a crack in reality. It does not mean everything we know is wrong. It means everything we know may be incomplete in a specific, measurable, testable way. That is far more exciting than fantasy because it can actually be investigated. In the end, CERN's crack in reality is not a tear in space or a doorway to another universe. It is something smaller, colder, and maybe more important, a stubborn pattern in the depths of mesons that the standard model cannot yet fully explain. It began as a whisper in an angular measurement, survived years of new data, outlived nearby failed anomalies, and now stands as one of the most serious remaining hints that particle physics may not be finished. Maybe charming penguins will explain it. Maybe better calculations will close the crack. Or maybe, hidden inside those rare decays, nature is showing us the first outline of a deeper law. So what do you think? Is CERN looking at the next great breakthrough in physics? Or will this anomaly join the graveyard like so many before it? Drop your theory in the comments. And if you want more stories where science gets pushed to the edge of what reality can explain, make sure to like this video, subscribe to the channel, and turn on notifications so you do not miss the next one.